Let's start. So we're going to complete this notebook with the BDT, and then we'll switch to the neural network, which will be the same data set, same thing, just for the neural network. So all right, so we reached up till here. We talked a lot about the ROC curve and the AUC. Next, yeah. So if you look at the ROC curve, it doesn't tell you which threshold to cut on, right? It says that overall, this is the performance for various different thresholds. You get a different performance. But in the end, what do we care about in high energy physics? Often it's the discovery significance, which we approximate with S over square root of B. This is the more precise formula for that. This is, of course, assuming you have no systematic uncertainties for now. Right, so we're going to use this formula to actually compute our expected sensitivity to the signal strength of the Higgs. So this is implemented in this little block over here, the Asimov significance. And how do you actually compute it? So actually what I'm going to do is run these cells, but I want to show you the plot here first. Okay, so this is a plot that's very, very common in analysis. What you're looking at here is the output of your BDT for as a function of so the output of the BDT for the background events and the signal events. So of course, it's trying to give a higher score to the signal and a lower score to the background. So the red, the signal is concentrated on the right side. The background is concentrated on the left side, but the classification isn't perfect, so that means you have background contamination even all the way up to almost the score equals 1, right? And here you see that the training set and the test set distributions agree pretty well, which means that there's not, sometimes they don't, when there's a little bit of the model has learned some features of the training set that don't generalize very well. Sometimes they don't. But here it's all right. And then the question is, if you were to make a cut, where would you make that cut? 0.6 looks like a good point where like you keep a lot of the signal and cut out most of the background. But in the end, you want to optimize this significance. So what you're going to do is compute the significance as a function of the cut. So you're going to go from left to right, and in each step, you're going to integrate from the right. Okay, so if you say the cut is 0.2, then we're removing all events less than 0.2 and only keeping the ones above. So the integration will be from 0.2 all the way to 1, both for signal and background, and that'll be the total number of events you expect after the cut, and then you can calculate the significance. So we do this up here in this part for various threshold cuts. And then we compute and plot the significance. So what do we see? We see that initially, as you raise your threshold, the significance goes up. And this makes sense because in the beginning, for a small increase in threshold, you're cutting away a huge amount of background. You can see, oops. You can see over here, each time you increase this threshold a little bit, you're cutting away a major amount of background, so it's your significance goes up. But at some point, you start to get diminishing returns, and then here you actually start to lose significance if you go any further up, because then you're cutting away signal as well. So often you can look at this plot and like take the peak and say that that's roughly where I want to make the cut, if you want to make a cut. And that peak will give you your expected significance, which is over here 0.82. All right. Does that roughly make sense? Yeah. It's unlikely that it'll keep on increasing because that would mean if it kept on increasing, it means the harder you cut, the more significance you get. But at some point, if you're cutting at score equals 1, it means you're keeping no events. So for sure, S over square root of b, where S and b are both 0, is not a good significance. So if if it keeps on increasing, it's likely you have a bug, or the problem is so easy to separate that it gives all the signals value 1.
1 and 0.
It's highly unlikely in a high energy physics data set where like you can get exactly the same event and it could have come from signal or from background, because the whole, like, we work in a quantum world. So if you get such a situation, you should probably check what you've done. There's probably a bug somewhere. Yeah. Yeah, okay. So then, like, your threshold can go a bit far, and then you might wonder, okay, this looks good for my this Z, but this computation doesn't handle systematic uncertainties, so how would it work? So these are the questions you can ask yourself. In the end, though, nowadays we don't use cuts that much. So this is just a way to estimate this performance of your model, and then you can use this to optimize your model. But in the end, nowadays, what we do is we take the output of the classifier and we fit it to data. So this is something we were discussing in the break. Maybe I can discuss it again. Where can everyone see? Is this a good place? Okay. So when you train a classifier, the function the model is implicitly trying to learn is this. So if S is the score given by this boosted decision tree or a neural network for some event which has multiple features, so I'm drawing an arrow on top, it's trying to estimate this. So that's the probability that this particular event, so if you could draw like a PDF of your signal model, which you can't because Monte Carlo simulations and detector simulations, you don't get a PDF at the end. But if you could, then this would be the probability of getting X for your signal model, and then on the denominator is X from your signal model plus X from your background model. So if you had a perfectly trained classifier, this is exactly the function it would have learned. And in the end, what we care about is hypothesis testing, right? So we want to, we do optimize all of our analysis so that in the end we can say, what is the maximum likelihood value of some parameter mu? And so we do this comparison of hypotheses H0 versus H1 and so on. And there's this lemma in statistics called the Newman-Persson lemma, which says that the best statistic you can use for hypothesis tests is the likelihood ratio, which looks something like this, is equal to P of X given your H1 over P of X given H0. So let's say your H0 is background only, and your H1 is signal plus background, right? So then you can see that this looks very similar to this, not exactly the same, but you can do some kind of S over 1 minus S, and you can go from one to the other. We'll see more this in detail tomorrow. So essentially what I'm saying is this function that the classifier learns is very closely related to the likelihood ratio, which is the optimal observable you can have for your hypothesis tests, which is why training classifiers is still useful, even though in the end, the real objective is no longer filtering out events. It's really to fit the entire output on the entire data that we measure. Okay. What do we have next? So then you can do some hyperparameter optimization, but this is optional. And with BDTs, you don't really have to optimize too much. In neural networks, you know that you can spend months optimizing them. So there's some extra stuff here that If you want to have a look at it, you can. There are some somewhat automated ways of doing hyperparameter optimization. But then a more interesting concept that I think that's worth going into is the learning curve. So I'm guessing some of you will already be familiar with the learning curve. Would you raise your hands if you are, just to get an idea? Okay, so that's less than half. So let's go through it. So I'm going to run it first so that we are quick. Oh, what's going on here? Output axes. Is there?
Maybe run.
But it's something over the text editor. Anyway, okay. While we're fixing this, what is the learning curve? It's this curve that gives you an idea of whether you've saturated the information that you have. So it's going to look something like this. So you have a model, you have some hyperparameters or whatever, and you train the model. Let's say this is one. This is all the training data you have. All right. So normally you would take your entire training set, fit your model. You'll get some. Let's say this is your AUC, right? Or your significance, whatever your performance metric is, and you'll get some performance here. Let's say that's 0.8. What you want to know is have I used up all the information like that is possible, or maybe if I had 10 times more data, I could have gotten even better performance. So if you don't have more data, one way to estimate that is train the model with less data. So you have one here, maybe you have 0.5, the fraction of the total training data set, 0.1, and then you might see something. So you might see something like this, that the curve is kind of flat here and goes like that. This means that, okay, so at some point, the more data you have, the better the performance gets, but then it plateaus. And then here at this point, if you even had like twice as much data, you would not get that much more performance, at least on the same model. Usually, nowadays, you see that if you have plateaued, or let's say you've plateaued already here, right? What it means is that your model is not expressive enough. So you can make a bigger neural network, and then you'll see that as the network gets bigger, your plateau gets farther away. So it's a good, just a way to understand how much data you have, how powerful your model is, and so on. Is it running? Yeah. For training, yeah. Yeah. Uh-huh. Yes. Yeah. So like you take your events, like they have weights. Like if you take half the events, I mean, even though they have weights, like the effective number of events is going down by half, roughly. Like if your sample size is 1,000 and your effective sample size is 900, you take half of that, it's just half. So everything still works. Like, yeah, yeah. So you will still see this kind of curve. It's very common to see this kind of behavior. Yeah. And usually, like when we make this plot, you can like say that, okay, the number of parameters is 1 million, this is 2 million, this is 3 million. So you get a very nice looking curve that shows both the scaling as a function of data and the model parameters. If there's a problem, maybe we can skip it for now because there's the neural network as well. Yeah. It's working in your notebooks? The learning curve. So you should.
They're working. I might have to restart it.
Yeah. Okay, so then if you run a few more cells, you should see the plot.
Might have to restart it.
Okay. Can someone send a screenshot of the plot on Slack? Okay. I think there was some disconnect, reconnect, or something. Okay. But anyway, we'll restart the neural network, so it'll be fine.
But yeah,
I don't want to worry about this. Yeah.
Yeah.
So, do you think nothing is going to work now, or will this
This
work?
will this
No, I think we need to restart. Okay. So let's go through it quickly. No. Do you have Slack? Somebody must have posted the picture. Yeah, awesome. Can we show that? Okay, yeah. So the thing on the right you see is roughly what I was I was trying to draw here. You can see that as the training size increases, the performance, which here we've measured as the AUC on the test set, goes up, 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 and then it doesn't plateau yet, but it kind of you can see that there's diminishing returns towards the end. And yeah, the same thing can be seen as ROC curves, where the more training data you give, the better the ROC curve is. Yeah, exactly, because this is not even 100% of the data. So you could probably, it could mean two things. One thing is that, which is rare nowadays, but if the number of features you give is very small and the problem is very easy, it could be that that's all the information there is, and then more data is giving you nothing. More likely, if you have a more expressive model, you can you can pull out more information from the data, or yeah. So then, if you look at the hyperparameter stuff, like GBM, it'll say there's a section on what you can increase for accuracy, where the number of if you reduce the bin size, it does more cuts and so on. So you might find a model that saturates better. Yeah, so it's something you can try, and usually, like at some point, you switch to a neural network and it's able to consume data much more efficiently. Yeah. Mm-hmm. Um, that's a mistake. There should be no 2 plus. Yeah. So if you look at the paper, if you go to the paper, we'll find the exact formula. I think, yeah, I don't remember there being a 2 plus. 2 times, okay. Yeah, that's right. Yeah, we C dot or something. Yes. Okay. So we talked about feature importance. So let's quickly have a look at that. So every BDT package provides its own feature importance. By default, it'll only look at the number of cuts the trees make per variable and count. Yeah. So if a variable has been cut on many times, it gets a higher importance. Better than that is what's called gain, where it's weighted by the gain you get after the cut. Because, yeah, as we said, like one feature can be used and have a huge gain, but used only once, and another feature could be used 5 times with a fractional gain. So this weighting is relevant. So this is the feature importance coming from light GBM, and then we see the permutation importance. Which only takes a few lines to compute, but you have to think about this carefully. Permutation importance, if you do it wrong, will give you it's something that doesn't make sense. So here, the permutation importance is computed for significance. So really, the numbers that you see in this plot are, if you were to erase the information of, let's say, this lepton PT1, then how much would the significance drop? So it would drop by about 0.4. Yeah, so the y-axis has a clearly understandable meaning. And where are these error bars coming from? Somebody asked me about the number of iterations, I think. So here we're doing permutation importance 3 times, and then the difference gives us this error bars. If you increase the number of iterations more, you'll see these permutation importance error bars shrink further. Yeah. But you can also compute this as a function of, for example, the AUC. So how much does the AUC drop for each of them? And interestingly, sometimes the permutation importance for AUC will be different from significance, because maybe one feature is not required to really do signal versus background, like pushing it between the 0.5 threshold, but is more useful in pushing an event from 0.7 to 0.9, which becomes more relevant for significance compared to accuracy, for example. No, if we do the permutation importance 100 times, we're just shuffling the feature 100 times. So the drop will be roughly the same each time. It's just the error bars you see right on top of the green line, that will shrink. But of course, you have to take these error bars with a grain of salt, because if your data set is not very big and you shuffle it many times, you're kind of evaluating on the same thing again. Yeah, this is statistical. Yeah, that's right. It just means that if you do the permutation many times, each time lepton PT will come out as the most important. It's the if you make a cut on the output of the classifier, everything above it. So if how many events will have a score above the threshold? Here we are not doing one single cut, we're scanning over the whole thing. So we're doing many cuts. Okay, so this is hidden inside okay. So are you asking for permutation importance or the plot? Here, yeah, so you can specify it in the package, but if you look at the documentation of the package, I think by default it chooses 0.8 or something. Okay. And okay, the big selling point of this is that you can do permutation importance on neural networks, and neural networks don't by default give you feature importance, so that's a nice thing. I think that's the end. It's a package. So scikit-learn has a permutation importance package, but that one does not handle things like significance. So this is a package. Full disclosure, this is my package. So I'm the maintainer for this package, but you can write the code yourself as well. But this is a nice way to do it. So okay, maybe we can go through the details of exactly what's given here. Yeah, so this is your importing permutation importance. So if you don't have it, it's just pip install permutation importance. It's very simple. And what are you giving it as input? The model itself, the test data set, as well as the true labels, any weights. And then here, n iterations is how many times you want to do the shuffling and do permutation importance. Okay, and then this is an important one. This says use predict proba, and it's true for light GBM. So turns out not all the packages have the same function. So for example, if you're doing Keras neural networks, the function is model.predict. Whereas for these BDT packages, it's usually model.predict proba, and then you have to put a bracket and say 1, because 1 is for signal score. So this is just telling the pack. So this permutation importance package can handle neural networks and BDTs or anything you've written yourself as well. As long as you tell it what function to use to do the prediction, it can take care of that for you. Yeah, and then here it's saying like what should be the metric to evaluate the performance. So here it's Asimov, I mean the AMS, but you can choose AUC or something else. And here you're just giving the column name so that this plot has meaningful names for the bars. All right, I think the rest we can skip. Yeah, there's examples with XGBoost and so on. If you're interested, you can try them out. I think we should move on to the neural network one. Right. So there's not. So this is going to be a similar, same data set, same loading. So I'm going to go quickly through the loading stuff. You already have uproot, and you can see how easy it is to load a data set from root into this format. So yeah. Why is lepton phi? I have not looked into a lot of detail of the actual physics problem, so I'll have to think about it. But yeah, there's probably some angle information that's used.
Why lepton phi is becoming important here? What an intuition. Just lepton phi.
Yeah, there must be two phis. Like a single phi is never useful.
We haven't used delta.
No, but if you have two phis, it'll compute delta phi.
With respect to the net.
Yeah, because in the feature engineering part, we do compute delta phi, right? So yeah. No, for a phi, you will never see it because the phi itself will look the same, but a delta phi will look very different. Yeah, so even if you give it raw phis, it will internally learn the delta phi. And so yeah, which is easier for a neural network than a BDT. Because if you look at if you think of a BDT, it's making a single cut at a time, and why would it use cut on phi when it has absolutely no improvement? But if it by mistake makes one cut, the second cut will be super useful. Or like phi 1, if it makes a cut, then phi 2 will suddenly become useful. Yeah. But in a neural network, it's a lot easier. So you need to do less feature engineering for a neural network.
In your setup, is it easy to do a scatter plot of, let's say, has phi met gone as an input, but other phi has gone?
Yeah, let's see. Plots. We had plots, no? Oh, there. Okay. Lepton phi. Yes, there are two leptons. There's phi 1, phi 2. Which plot did you want? Sorry? Yes.
So,
2, 3, 4, 5, 6.
If we want to see a scatter plot of met phi and lepton non phi, and
Okay.
weighted by and want to see which events got high score of the network.
Yeah, it can be done. I'm not sure if I can do it on the fly. Let me see.
The scatter plot before training? No, after training. The scatter plot in two input variables, the met phi and the lepton non phi.
And the color of the dots will be the score.
Where should be the score? Yeah, the score. Other notebook, right? Yeah, this one doesn't know.
Why not?
This is a near.
I'm already. Oh, okay.
We also saved.
X. I don't remember what they're called. Train. What's it called?
X train.
Is it?
Or if you maybe plot on this test.
Yeah. So which one is it? It's I guess 0.
And which of the pi was important?
First one should work. So it is 0, 1,
5, 0.
4. First of all, let's see this. Is this a data frame? Can I?
These are NumPy arrays now.
Ah, okay, good. So then I can just do this. Why?
or is it converted?
Where is white test? Where's the white test? Okay. There is. That's weird.
This is mid, I guess. This is 5.
Here the color is for signal and background.
Yeah, I'll put the scores, but I was hoping that the signal and background would already be on some diagonal or something, but they're not.
It depends. Maybe it could be there several things that will be in the two electrons.
Okay. Let's see. Okay, let's just be smart. Let's do this. I'm just gonna do delta phi. I'm pretty sure it's delta phi. Roughly, that should work.
X text.
Mhm. Yours doesn't autocomplete.
It does, I think.
Okay. There is some difference.
Maybe increase a bit.
Yeah.
His type density.
Just,
Step.
yeah. What- Yeah, okay, there's a big difference.
This is delta 5.
So yeah, so it's really delta phi that's quite useful. Sorry?
This is which delta phi?
Lepton 1 and lepton 2.
Electron one.
Yeah. This is roughly delta phi. I haven't done the pi like whatever the pi. Yeah.
Proper.
Yeah, yeah.
And then one should be able to see which area the network or BDT is giving high score.
Yeah. But scatter is too dense. Okay, how about this?
Here,
I have an idea. I think we can do some dirty thing. Why doesn't it order complete? Pred. Why pred? Why pred is the thing, no? Okay, good.
GPU.
Yeah.
Greater than
Okay.
0.5.
What am I doing?
So you're plotting score greater than 0.5.
No. made some mistake. Oops, what have I done?
Doesn't look that different.
Yeah, but how can we make it? Okay, I have another idea. Let's do this.
Scatter, we can reduce the size of the box.
But I want to try one other thing first. Let's just see this.
My way could be if one can see this block of the part on there and all.
Yeah, that's roughly what I'm doing.
We're cutting it.
Anyway,
What?
it depends on how much importance it is.
What's the problem? Okay.
Number of
So yeah, this is the closest I can do right now. So this is not signal in background anymore. This is signal region. So NN, the blue is NN score is greater than 0.5, and the orange is less than 0.5.
Okay, so it's showing that it's cutting out the background from the two sides. So it has sense that the signal is
In the middle.
So it's picking up those background events which are in the middle.
That's right. Yeah. Okay, so it's doing something reasonable. How much time do we have? We have half an hour. Okay. Okay.
So back to the neural network.
All right. So all of this stays the same. Splitting. I think here it's a bit more elaborate. We're doing splitting it into train, test, and validation, but all the concepts remain the same. Yeah, so standard normalization for neural networks is far more important than for BDTs. BDTs can, even if you have something at 1,000, they can make a cut. What have they removed? Which part? Okay. Yeah, so we have to fill in here the standard scalar. So you fit on the training set and then you transform the other two sets.
So those 3 lines you have to fill in. So yeah, you can just try on your own.
Considering we don't have too much time, I'm gonna live code. All right, and the weight scaling also we do just like before. Okay, here, have you guys? Yeah, I think you've already used Keras once, so hopefully this part is also easy. Just have to complete the network. We have. Okay. Yeah, we have. So you have the input thing and the first layer. Just add another layer in the middle and then an output layer. So I'm going to wait a minute.
So everyone here familiar with Keras and TensorFlow? I think so, right? Yeah. So the model is, partially defined here. You need to complete it and then run it.
Can someone tell me what I need to do next? What do I need to write below this line? Okay, yes. Cool. And then for the output layer, does anything change? Right. What do I make it? Okay, everyone knows, so it's good. All right. Patch norm? Sorry, who's talking? Can you raise your hand? I can't see. Yeah, this is super simple, dense
This is
network.
very simple.
You don't need any batch norm. Okay, so let's train it. So compared to the BDT, it's going to take quite a while longer. Oh, this is already here.
I didn't remove the plots.
Okay,
Plots are there.
but it's training and the plots already there. It's weird.
Yeah, because the plots I didn't remove from the previous one. Let them take some time because I don't need to rush.
Yeah, everything else is fine. Yeah, just the I want the permutation importance. Okay, while it's training, I have a question. Where we did the pre-processing, we fit the scalar on the training set and then applied it on the validation and the test set. Why didn't we fit it on the full thing? So let's look at, yeah, so here, yeah, so if you see here, we took the training set and we did the fit transform on the training set and only transform on the validation and test set. Why did we do it this way and not do the standardization on the full data set? Is there a problem in fitting on the test set? It's a subtle point. Like, of course, training on the test set would mean you can't use the test set to evaluate your model anymore. But even if you do the pre-processing, if there's anything to be fit to the data set, if you do it together on the training and test set, there's a data leak happening. So the transformation is it's adjusted for also the test set, and then you're kind of biasing very slightly the way you do pre-processing. Exactly. Yeah. So it's a very simple thing. All it does is calculate the mean and standard deviation and rescales it, right? So you would think if I do it on the training set or if I do it on the train plus test, it can't hurt too much, right? But there is a difference. The mean that's calculated, especially on a small sample size, will be different. And then, yeah. So there's a very interesting page that the Princeton University hosts, which they point out all of these mistakes when people do machine learning in science. This is called data leak. And there are like a list of things that are like small mistakes that people make when you're not a machine learning expert trying to do ML for science. Okay. So has anyone got this plot? Okay, awesome. Right, so yeah, it's a busy plot. So there are two y-axes, of course. So you can see that the loss on the training set goes down. And also on the validation in the dashed line goes down, which is good. That means we're not overtraining. Whatever it's learning on the training set is generalizing. And on the other, in orange, you see the AUC increases with training time, both on the training set and on the validation set. Validation AUC is sometimes higher, sometimes lower, is fluctuating. It's fine. Generally, it should be lower because the model will learn something extra from the training set, but these differences are fine. You see that at the end, at least for mine, the validation is lower than the training. If you overtrain it, like, okay, so let's look at an example of overtraining. But before that, okay, there's a little exercise for you. Can you get feature importances from the neural network? So all you have to do is go back to the BDT one and copy the permutation importance and bring it here. And then let's have a look at what the neural network is learning. Okay, so somebody has to help me through this. I've just pasted what I saw from the BDT. What do I put here? Is it model? Okay. I'm not even looking at the code, I'm believing you. So I say model. Okay, X test. What about this one, predict proba? All right. And what do I put for columns? Maybe I just, this, right? Let's see if it works. Okay, so we can see that it's predicting with the network many, many times. So this is 3 times. I've asked it to do the whole thing 3 times. And then but it's doing much more than 3 because each time it removes a feature, it has to do a prediction with this erase thing. So if you have 6 features, then it has to do it 6 times plus 1 for for when you don't erase anything. So a total of 7 if you want to do 1 iteration, and if you're doing 3 iteration, then you do the 6th thing twice more. Okay. So this is what I get. So you can actually get feature importances even for neural networks if you use permutation importance. The number of evaluations? So it should be, there are 6 features, right? Yeah. You need the actual one and then, yeah. So how many do we have actually? Yeah, there are 19, right? I see 19. That's what we expect. Yeah. The scalar. Yeah, it's good practice to fit the scalar or any pre-processing that requires a fit to do it only on the training set. Because like if your argument is that it's simple, then okay, it should be simple and you should learn it already on the training set. If you're going to use the train plus test set and your pre-processing is getting biased by the test set, then the evaluation on the test set will look better than it might look for real data where you don't know the distribution. So it's the same. It's just like if you actually train a network, then it's tremendously biased if you train it on the test set. But even if you do like fit the scalar, you are biased in a little bit, and you can do studies and convince yourself that actually makes a difference if you have a small training set, which you often do in an experiment. It really shouldn't. But like in a large data set, your training set is large enough, so you just fit on the training set anyway. So there's almost no reason to ever fit on the test set. Sorry, can you repeat louder? Sorry? You want me to scroll down? Here? Yeah. Yeah, so what's happening? Under the hood, so you've given the model and the test set to this package, and the package is evaluating it, but not just once, 19 times. Why? The first time it evaluates the performance just like without erasing any information, so on all, and it sees the nominal performance. Then it erases one column, right? It shuffles one column and evaluates the performance to see the drop in significance. But it has to do this for every column. So if there are 6 features, it has to do this 6 times. And then I've said the number of iterations I want is 3, which means 6 times 3. So 18 plus the original one, so 19. That's why there are 19 of them. 2 to 5, 6. I guess this must be the test set size. Or the number of batches in the test set. 'm I'm not sure. Yeah, it's the number of. Yeah, I think it's is evaluating in batches. I think. I think it's just the number of batches or something. I think it's like it must be batch size must be 32, and yeah, it must be evaluating in 32 batches at a time. I think. 32, like batch size of 32 at a time. 32, right? Yeah. Yeah, so that's what's happening. And then there's one left over. Oops. Number of steps, basically, yeah. Number of predictions. So yeah, this could probably be optimized and have bigger batch size, and the prediction would go faster. Okay. So now let's look at the same rock curves and significance. When does the session end? 5? Okay. Cool. Okay. So we see the rock curve, training and test are almost overlaying. Score distribution. So there's some funny business going on over here. So if I don't know about CMS, but if you were in Atlas, you would spend a month understanding why there's this bump over here. Yeah. Right, and then we see a similar significance curve to what we saw in the BDT, but looks like the Z max is quite a lot higher, right? It was something like 0.8 before? Yeah. For the BDT? Okay, yeah, so maybe we got a bad iteration of the BDT. Yeah. Okay. Usually, like for simple problems like these, the BDT and the network does similarly. You don't expect one to do better than the other. Once you start like putting in symmetries and stuff, the network will really outperform the BDTs. And if you train on low-level data, the neural network does a lot better. Okay, now just to get an idea, because usually in tutorials you only see things that work very well. Let's see what a overtrained network would look like. So we train it on much smaller data. I'm going to run through this quickly. Yeah, on Monday, Elham will do generative model. Okay, so I think, yeah, go ahead. Right. Yeah. So that's just this package has been made to support different kind of classifiers. So sometimes you have light GBM, scikit-learn, all of these packages. They usually use the term so model.predictproba to get the output for the score of the model, right? Because if you just do model or predict, it gives you only zeros and ones. It automatically chooses the threshold of 0.5, and all events above 0.5 are given 1, and below are given 0. The functionality of Keras, for example, is different. If you say model or predict, it gives you the actual score. It doesn't do any threshold thing for you. So depending on the package, you need to either use predict or predict proba. And so since this permutation importance package was made to handle everything, it takes as an input parameter whether, like, you can tell it that this is a model where you should use predict, and this is a model where you should use predict proba. So for light GBM, we use proba, and then for Keras, we use predict. And okay, so somebody was asking about the loss curve. So let's look at the loss curves for a model that's not very, that's overtrained. So here we can see that the training loss in solid blue continues to go down, but the validation loss after a small while stabilizes and actually starts going up, which means that whatever the model is learning on the training set does not generalize to the validation set at all. And the more you train, the worse it gets. So this is like the most extreme case of overtraining you can get. Usually things are more subtle than this. But also you can see with the AUC, the training AUC is going up, whereas the validation is not going up. Yeah. So then if we had time, you can try to like see how do you improve. If you have a overtrained classifier, what can you do? You can either do regularization or do something smart. With sometimes pre-processing already helps. Things like dropouts are very useful. So it forces the network to learn different paths towards constructing the same decision. Yeah. So these are the kind of things, and hyperparameter optimization are all kinds of things you can try. Okay. Yeah, I think this is the end now. So again, yeah, in the ROC curve, you can see the major difference between training and testing. This is obviously a big red flag. and you should improve your model. You get it what? Really? You're seeing this? It shouldn't happen.
Every time you trade, you see some random fluctuation.
No, the model will, but for this fixed model, the AUC should be the same every time. So you have a fixed model? Yeah, probably. Ah, was that a comment on dropout? Yeah, so you can evaluate this whole area under the curve that we talked about. Sorry? Ah, I mean, your number will be different from this because trainings are random. But you should definitely see, given how small the training set is, that you should see a similar pattern, right? On your laptop, do you see that the training curve is much better than the test curve? Really? You're getting a good classifier? Yeah. Ah, yeah, sure. This is random. Yeah. So good. You don't have to waste multiple months trying to understand. Is it this? Oh, yeah. You wouldn't know if it's the same in CMS.
Same everything.
Yeah. No, I mean, yeah, just yeah. In Atlas, we really want to understand every little bump feature. Yeah. Hmm. Yeah, often like sometimes it can be a physical thing, like that at that point a subclass of events suddenly become easy to classify. Right. Okay. Okay, yeah, go ahead. If it fluctuates, your validation loss will probably fluctuate because one is we like to train on as much data as possible, so our validation set is usually very small. So you will see fluctuations. You should, yeah, a lot of people when they plot loss curves, they use a smoothing function. So if your true loss is like this, they will like put some what is it called, rolling average, so that it looks a bit smoother, and you can actually tell whether it's going up or down. Because if it's super fluctuating, then you can't tell anything. But yeah, so sometimes it's, especially if you train generative models and stuff like GANs, it fluctuates so much, it's very hard to tell if it's going down or not. So then you need to do a lot of smoothing, and then you see that it's very slowly continuing to go down. Yeah. If it's not, if it's still going down, it means you should train more. If you train more, you would get better performance. Yeah. So one of the things people use is early stopping, which is you set the number of epochs to some huge number, and then you just say that when the validation loss stops going down, you just kill the training early. Any other questions about what we've seen? Did did you manage to get the feature importance for the network? Okay, cool. Does it look similar to the BDT, or is the neural network finding different features important? Sorry? It's better. Sorry, I can't hear you. Can you be louder? Uh-huh, yeah. For you, it's better than neural network? Yeah, you can use more. Yeah. So, yeah. I'm going to come have a look at your plot. Let's.
So this is my BDT.
Yes.
Neural network spec.
Mm-hmm.
I expect this will fall, right? You know.
That's right.
But here you see also this.
Yeah. So there's this phase space in the background.
Here I also see there is a
Mhm.
BDT also.
So probably, so if you train it a few times and you always see this, it probably means that there's some phase space of the background that looks signal-like, and so it selects it.
I mean, it's okay, like it's
Yeah.
There's nothing that I have to worry for, right?
Yeah, you should like just convince yourself that it makes sense. You could, if you want, you could cut on this phase space of the background. You could cut on, select events in this region, and then plot them and see if they fall in some.
What they looks like, you know,
Yeah.
basically I will map this out and then go to the
Yeah.
input features, like, you know,
Exactly.
what exactly is happening.
Exactly.
This is fine, but now if I have some, like, you know, I have seen 2-3 peaks sometimes in the background distribution, for example. So in that case, how to, like, you know?
Yeah, you should. I mean.
I mean, there are some. Let's say, okay, I expect that background will, you know, be on the left,
Yeah.
on the be highest, and then it will be monotonically falling third.
Yeah, it could have multiple peaks. Like you could have 2-3 sources of background, and some are super easy to classify, so they get their peak, and then some of them are a bit harder, so they have a separate. So there could be subpopulations that. So you usually you don't see two peaks, but you'll see like a peak and a shoulder, and then a
And then,
yeah. So it's not uncommon.
It also happens, you know, sometimes when you, like, if you really, like, you know, let's say you remove some of the background input features.
Yeah.
So
Or then it
sometimes
goes away.
It gives well, like, you know. But
Yeah.
you know, it's a cost and trade between the performance and also, like, you know, how the shape is coming.
Yeah, but the shape, I mean, I wouldn't remove features because of the shape, because the features are actually giving the model power. As long as you convince yourself that that shoulder makes sense, that there's really something in that feature that becomes useful, and it's fine. Usually it's fine. Yeah. Oh, I will also show you some new diagnostic tricks tomorrow that allow you to really see which features the model is learning and which features the model is not learning. So you can actually use the classifier to reweight your background in a way that it will reveal which parts is not learning properly. So we'll see that tomorrow.
For example, here for the, if I look at the spectrum, they don't goes to one actually. Like, it's
Yeah,
saturated
it
1,
happens.
8, 9.
It happens. It's very normal.
Feature important.
Yeah.
Most important is given to electron PT1.
Yeah.
But if I see
It's not the same. That's very interesting. So why? I don't know why, but we should understand. So either the neural network is learning something different from the BDT. You should, maybe you can train it a few times, both of them, and see if it's always different or not. But if it is, it could be, because there are very different learning algorithms, so they could be focusing on different things. A lot of the time in Kaggle competitions, what they would do is they would train different kinds of machine learning models and aggregate them to get the best final result, because sometimes they saw that the neural network catches some kind of events better and the BDT other kinds. So when you combine them, you get an even better performance.
like, for example, when we do a specific analysis,
Hmm.
we should use BDT and should use Nayak, because
Yeah.
they both are performing differently, right? If
Hmm?
I go by this example.
Yeah. So you would train it. I mean, what do you care about in the end? If you care about your sensitivity, then you look at your significance, and the one which is higher is the better one.
So it's basically trial and testing.
Oh yeah.
You look
Yeah.
at the
Yes, in
Predefined answer to this question.
no, yeah, there is there is stochastic gradient descent for neural networks, and then there's grad student descent for finding the best model. Yeah. 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 Which bars? Oh, they will change. I mean, the feature importances will also change. Yeah, it'll change. I mean, for one train network, those are correct. But if you train another network, it might learn a different way of doing classification, so it'll not be the same. Yeah. It should be similar because fundamentally the physics is the same. So some features are going to be more important than others. But in the second order effects, you will find that one model finds this more important than the other one. The neural networks like very nice, smooth distribution. So you will also find that if you change the pre-processing, the neural network might find. So if you have a feature like if you have a feature that looks that like the histogram looks like this, these are very hard for neural networks to learn. So often, or let's say you have like this, right? Then often like you want to do some kind of log transformation or something to make it. So neural networks ideally want roughly Gaussian looking features. So if everything looks like a blob like this, the neural network will do great. But as soon as you have a blob but like a second peak here, often you'll find that the neural network learns this very well and completely ignores this. So things like that, then you have to be very smart about pre-processing. So maybe this can be encoded as a one hot vector instead, or something like that. Yeah, and this is not so important if your end result is just classification. But if you are going to do statistics, which we'll learn tomorrow, then you will be getting the likelihood from the network itself, right? So then you don't have histograms and stuff. And then you have to be very careful. Just a second, sorry. Then you have to be very careful about that the output of your classifier is trustworthy. And then you spend years making sure all the features look somewhat Gaussian and the network learns every little detail very well. I think he had a comment, so let me just get and then come. Yeah. For what? This? No, it's. I've seen it to be true for everything. The ReLU, Swish, like Swish is a generalization of ReLU, and even for that, in the end, so like I'm not saying it won't work, but I'm saying uh, it'll work better if you do the pre-processing smarter. And even Adam really helps with not having to worry about pre-processing because it has adaptive learning rates and stuff. But even then, like so tomorrow we'll see likelihood-free inference, and there you'll see that everything looks nice, the ROC curve looks nice, and then if you look at detailed diagnostic plots, you'll see small places where the network hasn't learned. And there, yeah, I mean, I've spent months and months trying to get it to work. Also, for example, no matter how much pre-processing you do, the network will not learn perfectly. So what you have to do is ensembling. So you have to take like 100 networks, train on the same thing, and then the combined performance is better. This is a typical trick in simulation-based inference, where the output of the network is considered is used as a likelihood, and there you have to use ensembling to make to construct trustable likelihoods for deep networks. Yeah, but we do it. We do it. Like yeah, we can chat more about that. We use both flows and classifiers for likelihood estimation, and it's very expensive. And we use at Berkeley we have the supercomputer which we have to use for all of this. Yeah. Okay. You want to end it? What variables? Discrete, yes, yes. Oh yeah, yeah. Pre-processing is everything for neural networks. It's probably more important or as important as architecture decision. So if you have depending on what kind of discrete variables you have, like one-hot encoding. Do you guys know what one-hot encoding is? It's super important. Yeah, these are like they're not like glamorous, but it's very important to. So like earlier I talked about categorical variables like GGF region and VPF region, let's say, and I don't know, VH region. So these kind of things for neural networks can be encoded as one hot. So a one hot vector would look like this, where it's 1, 0, 0, right? And then for VPF it would be 0, 1, 0, and then for the other one it would be like this. Right? This has been seen to be quite useful representation of this kind of data compared to just having an input that's like 1, 2, 3. Compared to that, this works a lot better. There are even more generalizations of this, which is to broadcast this and have copies of this, like 100 copies of this, and then the network learns even better. But basically, this is a reasonable one, and this is the standard one. Then you can have, for example, you might have, how many jets do you have in your, right? So you can have 1 jet, 2 jets, 3 jets, whatever. So then you don't even want to do that because that doesn't fully encode your information. So you can do something like this. So if you have 1 jet, it's 1, 0, 0. If you have 2 jets, it's 1, 1, 0. If it's 3 jets, it's 1, 1, 1. You have to think a little bit about what seems like a good representation of the data and encode it that way. Won the neural network? Bias towards what? Yeah, so here, so the neural network is doing a whole bunch of matrix multiplications, right? So, and it's very hard for neural networks to learn exact zeros. So you'll see that if you need the network to predict 0, that's the hardest thing. So when you do, for example, generative modeling and you need to predict exactly 0 energy in a cell, that's one of the biggest challenges in generative modeling. So the easiest way to zero out information is to provide a 0, and then you can just take this 0 and the network will multiply this, right? Because you know how MLPs work. So the 0 can zero out an entire section of the big computation that the network is doing. That's why this kind of representation, I mean, this is all hand wavy, but this is the intuition for why these zeros are useful. I can't hear, sorry, I'm getting old.
I suppose GGF has also categories in that, like 1 jet, 2 jet, 3 jet category, and then VVF also. Then how will you combine them?
Yeah, you just think about it. Like, if you can have GGF region like this, and then you can have the jet represented like this, and these two can be together they represent everything. Together you can have GGF 1 jet region or VPF 2 jet region.
No, by matrix multiplication or something, or just different. I mean, the representation will be.
Yeah, you can represent them like this. In the end, there's no one good answer, right? You try something, this makes intuitive sense. This is something that we've tried and works. You might find some other representation that works better.
If I want to, like, GGF has subclassifications as 1 jet, 2 jet, 3 jet, then
right. So I mean, the
GGF
simplest.
will have 3 layers to it.
There are no layers here. So this is one variable that I'm representing as 3 input variables, right? I'm just converting one variable into 3 just because it's easier. So instead of saying like 0, 1, 2, I'm just saying this can only be 0 or 1 if it's GGF. This is 0 or 1 if it's VBF. I'm making it bigger, but it's fine. And so total you'll have 1, 2, 3, 4, 5, 6. So I'm converting 2 variables into 6 variables. It's fine.
you have that package that was for permutation, right?
Hmm.
Does it within it has an optimizer or it does not?
What optimizer do you want?
Any optimizer? Do you have?
No.
Because
It's a very simple package. It's
how is
something
it
you can write
batching then?
yourself.
How is it batching?
How is it?
Batching.
Yeah, so internally it does model.predict, right? And it does model.predict.
Yeah.
Right? You give the model and you say the predict function. So you do model.predict x test. That's what's happening internally. And so the default batch size for Keras is 32, so it uses 32. But yeah, we could update it to something. Yeah. Yeah, but now when this package was made, we had no other way to do permutation importance. Now scikit-learn has a permutation importance thing. It's just that it can only do it with AUC. It can't do it with significance, which is relevant for us. But